So welcome today for our seminar. We are happy to have here our guest, I may say, Mateusz Lango, who spent some time here on his ERC grant, and Ondřej Dušek is his, I don't know how to say, not so supervisor or colleague or nevertheless. So welcome. And we are glad that we have the opportunity to listen to your talk about more faithful natural language explanation. So the floor is yours.
Hi, yeah, thank you very much. Well, my name is Mateusz Lango, and since it's my first time here, I decided to even prepare one slide about myself. I'm the postdoc of Ondřej Dušek, and I completed my PhD degree almost 2 years ago at Poznań University of Technology, where this was the topic of my PhD thesis, which is very long and complex. But in short, I was working on imbalanced classification techniques, which is a purely machine learning topic. I was typically working with the tabular data, which is, well, not as cool as text or images, but still it is used in many companies and in many areas in business, finance, and even medicine. Fun fact about me is that I also speak Spanish, which was useful when I was internship here at ÚFAL some years ago, when I was working on the morphological derivations for Polish and Spanish. And well, currently I'm trying to learn Chinese, which is considerably a bigger challenge than just learning Spanish. Okay, so going straight to the topic of my talk. As I'm sure that everyone has noticed that in the past few years, we have observed a very rapid growth in the AI techniques and in general in the performance which we obtain by the AI models. And we started to move the techniques from the laboratories to the industry. But unfortunately, this transition is not as smooth as we would like. One of the problems which we encountered is that the models which we are working with are the black box models, and we actually don't know how this model works. So, for instance, if we are deploying a system in a bank that assesses whether to reject or accept a loan application, our customer not only wants to know that he was rejected, for instance, but also he would like to know the reasons why he was rejected. And currently, the black box models are not able to offer them this information. Similarly, if we try to deploy the models in the medicine area, the doctor not only wants to know that basing on this X-ray image, we suppose that our patient has a certain disease, but also the doctor would like to be sure that we have some real medical knowledge in the model, that we are not just exploiting spurious correlations, etc., etc. That's why in recent years, there is also another, let's say, subfield of AI. Another subfield of AI has emerged, which is the explainable AI techniques. This is a very broad term, which encompasses techniques like symbolic regression with some fancy genetic programming algorithms. It also includes investigating how the model works with probing techniques, where we want to learn what kind of the information is embedded in the hidden representation of the neural network. And finally, it also concerns the techniques to explain why the model performed a certain decision. So why I would like to provide explanations of AI model decisions. So first of all, there is ongoing debate how to regulate AI. And even though these regulations are still in progress, one of the proposals of EU to let's say allow the AI use in some disciplines is the so-called right to the explanation. So we must offer the user the explanation, or otherwise we simply cannot deploy the AI model in certain areas. Then, if we want our doctor to trust an AI system, then definitely providing him with an explanation how the model works and why he classified or made a certain decision, well, it certainly will help in build his trust in AI. And finally, we as an experts are also interested in knowing how our model works to gain some insights and create maybe better or more robust models. There are multiple forms of explanations, and one particularly interesting one for our today's talk is our natural language explanations. There are several advantages in comparison to other techniques. So the most important for me is that the user do not need any training to understand the natural language explanation. So for instance, if we are trying to explain image classification with something like saliency map, we can show to the user this beautiful image full of red dots or full of red dots, orange dots, etc. But at the end, the user don't know what these dots mean. We need to provide him with some training, with some information, how should he interpret this kind of image, etc., etc. On the other hand, if we have a natural language explanation, the user, as long as if the user is capable to read, well, he's also able to understand our explanation if we have generated like a nice grammatically correct text. NLEs are also repeatedly reported as a human-friendly method of explanation. At the end, this is how we humans typically justify our decisions. And finally, they can also be used to support conversation with the user in a setting with a dialogue agent. So how a typical natural language explanation method works for the task of recommendation. So in the setting of the recommendation system, we have a user, and we try to model his or her preferences, and then we have an item with certain properties. And our recommender tries to measure how well this item is aligned with the preferences of our user. Of course, there are many, let's say, problems how to deploy such a system. For instance, how to avoid the so-called cold start problem, how to make the search for the best item, computationally efficient. But of course, today we are not focusing on that factors. We just will focus on how to generate explanations of the recommend. So a typical explanation method for the recommendation engine is just some kind of fancy language model which generates text conditioned on the user, on the item, and on the decision of the recommender, providing us with text. For instance, this movie, well, you should watch this movie because, well, your favorite actor is in it. Okay, so how these systems are evaluated? If you look for a typical paper which evaluates explainable recommendation systems, then usually you will see something like this: a huge table full of numbers and full of metrics. A typical paper in this area uses about 14 to 15 metrics, which measure different aspects of the explainable recommendation. These aspects include quality of the recommendation, diversity of generated text, how well the text is personalized for a given user, what is the text quality. This is usually measured by comparing the explanation to the gold standard in the data set, etc., etc. So at the first glance, this evaluation seems quite, well, robust. The explanations and the recommendation is evaluated from multiple perspectives. But at the end, we were going, this is like a real story from PUT. We wanted to use this recommendation system to some of our projects. So we decided to perform some manual evaluation. We randomly sampled 60 examples of one of the, at the time, state-of-the-art approaches, Peter Plus, and what we have found. So probably we have found some typical errors, so problems with fluency. We found that in some explanations we had some phrases which was repeated over and over. We had some sentences that abruptly ended, and well, this was very unnatural, and certainly some more words were needed to complete the sentence to be like fully grammatically correct, etc. And at the end, we also found that some sentences, some explanation didn't have proper context. For instance, the first sentence of the explanation was, they also have a great dessert section, which, well, is maybe a good second sentence of an explanation, but not the first one. And finally, we found some explanations some explanations that don't contain rationales. For instance, hotel is great. This is nice verbalization of the 5 out of 5 star recommendation of an engine, but unfortunately, this explanation is not providing any reasons behind the decision. So this stuff is pretty standard, and we can probably solve some of these problems with standard NLG tricks. For instance, we can use more advanced language model to avoid some problems with fluency. We can get rid of repetitions with more fancy decoding algorithm. But actually, none of these reasons is the reason which was is the problem which was most frequent in our evaluation. The most frequent problem which we found, and in fact, this was the problem which occurs in 1/4 of the evaluated explanations, was the lack of prediction-explanation coherence. What does it mean? Well, we talk about prediction-explanation coherence when the reasons provided in the explanation do not align well with the prediction. So for instance, the recommender is saying me, well, you shouldn't choose this hotel. Why? Because the staff is very friendly and helpful. Well, does the model suggest that I like hotels where the staff is rude and unhelpful? Well, or maybe, well, you shouldn't see this movie. Why? Well, because the cast is very good. So unless the goal of AI is to mock my bad taste in movies, these explanations are terrible. And also, as one of our motivations, we are talking about users, about building trust of a user in an AI system. Unfortunately, seeing such explanations is probably not only not building trust in AI, but can ruin it. If we look at the schema, the figure which we saw earlier, the occurrence of such explanations is of no surprise. Why? Because on this schema, there is one very important arrow missing. And this is the conditioning of the text generation based on the recommender itself. If we want to explain how the decision was made, we should take into account the decision process which is happening over there. But unfortunately, the methods are usually conditioned only on the input and the output of the model. And the question how to condition the text generation basing on the internals of the model is relatively a tricky question. If we consider explanations, we usually should think about two properties of a good explanation. The first one is the faithfulness, and the second one is the plausibility. Faithfulness is it measures how well the explanation reflects the inner working of the system. So whether the reasons which are provided in the explanations are the real reason why a certain decision is reached. On the other hand, plausibility is more subjective, and it tells about how the user likes our explanation, whether it thinks that this explanation is trustworthy, whether he or she is convinced by the explanation. So just to give you two examples, an example of a fully faithful explanation, which is unfortunately not plausible, is giving the user the whole equation, how the neural network computed the result. So of course, this will be like extremely long equation full of softmaxes, weight multiplication, relus, gelus, etc. And if we provide this to the user, well, this is how the neural network truly computed the result. Unfortunately, even the experts are not able to understand this equation. On the other hand, if we ask about plausible but not faithful explanations, then these are the NLEs generated in a way which I talked on the previous slide. If we have as a model A explaining model B, but the model A has no interaction with the model B other by the decision, the model is not aware about the decision process in any way, well, the story which the explanation method generates can be very plausible, but unfortunately, it has no relation with the reality, with the real reasons which the recommender takes into account. So if the NLEs are as terrible as it seems, maybe we should give up on them and try other methods. Unfortunately, other methods, or at least many other methods, also have similar problems. Some years ago, very popular method of explaining image classification were the saliency maps provided by gradient-based methods. So for instance, here we have the image of the bird, which is classified as a bird. We are lucky. And then we are having this fancy image of the saliency map of gradients, which are inside the model. And we can say, OK, the model decided that this is a bird because it detected eye, it detected wing, etc. So some people find this explanation convincing, others not. But either way, these were very popular techniques which were used in many applications. But what is the faithfulness of such a visualization? What will happen if we will randomize the softmax layer, the final layer of the neural network? If we randomize the weights of the neural network in the final layer, the neural network obtains random accuracy, the accuracy on the level of the random guessing. So such a neural network is not able to tell us that this is a bird. But if we run the explanation, if we produce explanation for this new neural network, the explanation is almost the same as for the original classification. We can even increase the randomization in the neural network, randomizing the convolutional layers, etc. And still, we are seeing very, very similar explanation, which clearly shows that this kind of visualization do not show how the model really attains or predicted or make the decision. In fact, this paper, which is cited below, showed this worrying property for about 9 methods, and all of them were based on gradient propagation. So when we think about explanation methods, we should consider them as certain trade-offs between faithfulness and plausibility. There are, of course, interpretable models, which are very faithful, but if they are obtaining high prediction quality in most of the application, then usually they are as complex that they are not plausible. Then we have very, very high faithfulness neuron attribution methods, which have mathematical properties, etc. But they are offering explanation in a form of the importance of the attribution of a neuron in making the final decision. So we are only able to sort the neurons inside the model from the most important one to the least important one. But this is a useful information maybe for an expert, but definitely it's not a plausible explanation for an non-expert user. Then we have some local explanations that train surrogate models, which are only the approximation of the real decision process. And finally, we have NLEs that are usually very plausible, but not faithful. Of course, not all NLEs are as bad as it's showed on this picture. There are, for instance, NLEs produced by so-called gray architectures. These models usually consist of on 2 parts: the black box part and the white box part. And for instance, in this case, in the example which we see in the slide, the final decision of the model is performed by a fully interpretable linear classifier. Features to those linear classifiers are similarities to phrases which were extracted from the training set. So this is how the model really performs the decision, by comparing your input text with the phrases which are modeled by these prototypes. But unfortunately, this kind of techniques require rebuilding your classification model completely, which affects the performance because the gray models are almost always not as highly performant as the black box one. Then there is no text generation process because you only extract some phrases from the input or from the training set or from other sources. From other sources, there are also some NLEs that claim faithfulness by attending to parts of the inputs while generating text. Unfortunately, it seems that in general, attention is not a good explanation. There's an ongoing debate and the series of papers starting from attention is not an explanation, attention is not an explanation, attention is not an explanation. So let's say that this is debatable if this is a real faithfulness or a really good explanation. Okay, so in the next part of my talk, I will focus on two tasks, on the recommendation and image classification. I will first finish my story about the recommendation engine, and To improve the prediction explanation coherence, we proposed a new task, which is relatively simple, doesn't need any additional data annotation, and improves quite significantly the prediction explanation coherence. And then I will talk about image classification, where we proposed a pipeline approach that provides quite faithful explanation for this task. So, starting from the recommendation, we have proposed a new architecture, which is built upon previous state of the art. The transformer architecture at the input gets the user ID, item ID, some features of the item, and the later part is just the standard decoding part where we add the next token, the generated text. The transformer is a little bit more complex than usual because we have the first part, the first two tokens, they are there to compute the embedding of the user and item, which is later used to predict the rating. So here we have a standard attention as in the decoder transformer, whereas for the later part we have a standard decoder. So the masking of the attention is a little bit different than in a standard case. So how this method is trained? The method is trained on 4 tasks. So first of all, we try to predict the rating. So how well the user preferences are aligned with the current item. Then we have the context prediction, when we predict the words of the explanation in a scheme-gram manner. This is found to improve diversity of generated explanations. And finally, we have the standard task of text generation, which in our case is an explanation. And the final task is explanation-based rating estimation, which is a new task which we have proposed to improve the coherence. So how this task works? We claim that given the text of the explanation, without knowing anything about the user, without knowing about the item, we should be able to roughly guess what is the right rating predicted by the recommender. So for instance, if I'm seeing an explanation, this is a great movie, your favorite actor is in it, I can guess that the rating predicted by the recommender should be around 5 up to 5. And this is the intuition which we try to embed to the model during training. How we achieve this? So we have the standard rating prediction head, which basing on the user and item, which uses the representation produced by the transformer, which had at its input user and item. And this is the standard rating prediction head, which we use for testing, for measuring the quality of the recommendation, etc. But then we have a second rating prediction head, which tries to guess the rating predicted by this head only on the text representation of the explanation. In our case, we generate the explanation, then we compute hidden representation of it by performing pooling over time over all its tokens, and then we predict the rating. This rating prediction head is not trained to follow the gold standard of the data set, to not learn the gold standard values which are provided in the data set. This head is taught to follow the current prediction of the model. So the loss function penalizes the deviations from the model output, not from the gold standard. Okay, so what are the results, how good this method works? So we performed an evaluation on 3 standard benchmarks, which are used in the recommendation setting. And we employed 2 annotators, which provided a binary decision, coherent, not coherent explanation for 1,800 randomly sampled pairs. And 3 types of explanations were evaluated. Once, of course, the first type was the explanations were provided by our method, by the previous state of the art. And finally, we also evaluated the coherence of the so-called gold standard explanations, which are provided in the datasets. Our work with annotators were divided into 2 stages. In the first stage, we asked the annotators to annotate 100 100 explanations, and these were the same 100 explanations. Then we compared the differences, and this helped us to refine our annotation guidelines. And finally, we obtained the inter-annotator agreement at the level of 96%. Since we get a data set of annotations, we decided to use it to propose a new metric that would measure the coherence between prediction and explanation. We haven't used anything very fancy. We trained a standard Roberta model. At the input of this model was the explanation plus the numerical rating, and to fully exploit the pre-training of the Roberta model, we have converted numerical rating into text based on some fixed templates. So for instance, the rating of 5.0 was converted into very high alignment. Okay, so the results. Do not be worse from our competition. We also produced a huge table. And in this huge table, we demonstrated that our recommender is obtaining similar quality of recommendation as the other methods. We also, on the other metrics, well, on some metrics, we are slightly better than the previous state of the art. On other, we are slightly worse. But in general, we are quite comparable in terms of recommendation quality and the previously used metrics for measuring the explainability of the approach. So now the biggest question is whether we were successful in improving the coherence of our explanations. And the answer is yes. We were able to improve the coherence from 3 to even 8%. At this plot, you can see the red bars, which is the previous state of the art, the blue bars, which is our method, and the gold bars, which is the gold standard. And surprisingly, the gold standard is not as good as it seems. Particularly for the TripAdvisor dataset, the gold standard explanation were even less coherent than the explanation provided by any of the methods under study. This is kind of interesting and shows how neglected the issue of prediction explanation coherence was previously, because these datasets were produced automatically via using several heuristics, and apparently none of these heuristics took into account the coherence. So there are some bad news and good news. Of course, the bad news part is longer because I'm Polish and we like to complain about everything. So the good news is that we found an overlooked issue of explanations produced by explainable recommenders. And this is nice because we could write a paper about this. And we were also successful in finding a new learning task that do not require any additional data annotation. And in fact, it could be used with many other architectures than only the one that we have proposed. And hopefully, this new learning task should improve coherence without degrading the results on the other metrics. The bad news are that we cure the symptoms, not the disease. So, of course, lack of coherence is a good indicator that the explanations which we are getting have poor faithfulness. But on the other hand, even if we would have obtained a full coherence between the prediction and explanation, this gives us no guarantee that the explanation is faithful. Maybe we just learned to produce more convincing stories about how the decision was taken. And the second bad news is that the gold standard explanations are pretty bad and not faithful. And in fact, if we think about this for a moment, the explanations which are provided in the dataset, they are almost never, or they cannot be faithful. Why? Because usually such datasets are produced by people seeing an input and the desired outcome, and they are writing an explanation, or they are giving reasons for this decision, how they would decide it, that this input should be in this category or should get this decision. But this is how they would do this, and not how the model does it. So unless we have the model that perfectly reflects the decision process of a human, then actually this explanation is not faithful by design. So at the end, it would be nice to propose methods that condition the text generation on the inner working of the model to provide much better faithfulness. And also, it would be desirable to propose methods that do not need a data set of explanation. They can use some kind of, maybe several examples of an explanation to learn what is the structure of the explanation, how many sentences it should have, maybe what kind of rationales are given, but we can learn from them the style and not the content. And of course, I'm talking about these two issues because we tried to solve them in the next part of my presentation. So for the pipeline approach for the image classification. So one of the takeaways from the previous experiment was that we want to condition the text generation of the inner working of the model. And actually, how we can know how the model works and how we can condition the text generation on, on this how the model works. Well, the techniques which allow us for understanding the model better are actually the explainable AI techniques. So which techniques are the most faithful? Of course, the most faithful are interpretable models, but then we don't need explanation at all. And the second most faithful techniques are the neuron attribution techniques. These techniques sort the neurons from the most important one to the least important one. But unfortunately, this is an information which is understandable for an expert, but not for an end user. So our idea is quite simple. What if we would try to combine the natural language explanations to get a good plausibility for the provided explanations, and at the same time to get the knowledge about how the model works using neuron attribution techniques, which are highly faithful. And this is our idea. We proposed a pipeline that combines highly faithful neuron attribution techniques to investigate how the model works. And then to obtain high plausibility, we use LLMs to generate a description in natural language. The approach uses instruction tuning of LLMs, so we need only one example of how an explanation should look like, and no data set of explanation is needed. Additionally, we also do not change the architecture of the classifier in any way. The only assumption which we do is that the neural network is a convolutional neural network, which in case of images is probably quite reasonable. So this is an example of explanation produced with our approach. We have here, this one nice image, and then we have a story how the model arrived with the conclusion that this is a lakeside. The model classified this image as lakeside because it detected water in the lower half and the bottom right corner of the image. It also noticed volcanoes and mountains in the upper half and walkways at the bottom left corner and bottom of the image. And well, this is kind of nice story how the model made the decision, but how do we know that the model really made the decision in this way? And this is why our method is interesting, because actually we know that looking basically in the background what is happening when we generate this explanation, we know that the predicted class was this one, and the most influential neurons were neurons, let's say number 14, 37, and 102. And what these neurons know to do, what they are doing, what kind of a visual pattern they are detecting. Note that these neurons are in fact convolutional filters because we are talking about the convolutional neural network. So these neurons are specialized in detecting water, volcanoes and mountains, and walkways. In which areas these neurons were activated? Well, exactly in these areas which we mentioned in the explanation. So this is not only a very convincing story how the model arrived with the decision, but it is also rooted in how the model really performed the classification. Okay, so now let's go to the details and how the approach works. So the step one is quite obvious. We perform the classification, and we learn that on the picture we have a fountain. In a second step, we try to know which neurons were important or the most influential to arrive with this decision. Let's say that these neurons were the neurons 3 and 5. We get this information by using an algorithm layer-wise relevance propagation, which I will shortly discuss in a minute. In the next step, we try to gain some knowledge about what these neurons are doing. And for that, we are using a neuron annotation tool that looks for images that make the selected neuron highly activated and describe this visual pattern. In the fourth step, we are computing the activation map of a neuron and to see, in which part of the image the convolutional filter was highly activated. At the end, we convert all this information which we have gathered during this process into a very simple meaning representation, which in our case is a simple list of neurons and a predicted class in a form of a JSON item. And this meaning representation is then converted, in our case with GPT-4, to an explanation that the model classified this image as floating because it detected gushers of waters, etc., etc. So now I want to briefly talk in detail about two steps, about the LRP and about the neuron annotation tool. LRP is a method which is quite well established. It was proposed 10 years ago, and since then it was used in hundreds of applications, and it was extended in different directions, and there are many variants of it. LRP is so popular because it has several mathematical properties which make it really faithful to the decision. So how the LRP works? So first, we are doing a standard forward pass to establish what is the output of the neural network, and then we are doing an additional backward phase. In that phase, we are distributing the value of the output towards the neurons in the previous layers. So we are establishing, for instance, the logit for the correct class was 5. Okay, and which neuron contributed the most to this value? And we can use a very simple equation for that layer to establish these relevance scores. Of course, while we are progressing toward more complex layers, we should use different so-called local propagation rules, which are especially designed for different types of layers of neural networks. One of the important mathematical properties of the LRP is the conservation property. We know that the relevance which enters the neuron is equal to the sum of relevances that outputs the neuron and goes to the neurons in the previous layers. So actually, the relevance of neurons in a single layer is always constant and equal to 1. How the neuron annotation tools work? So we applied Milan, which is a method that works into steps. First, we find images in the training set that have image patches that make the neuron highly activated. And basing on this several images, we are producing a textual description of that pattern, maximizing mutual information. And here is one example. We have a neuron which was highly activated for such image patches in the training set, and basing on the set of such examples, we are producing the description of the pattern. In this case, it's faces of people. Okay, so let's go to the evaluation of our pipeline approach. We used the ImageNet dataset and the classifier ResNet 18, which is the smallest classifier from the ResNet family. But our research was not about getting the highest accuracy, but we just wanted to test out the different explanation methods. The baseline which we are using was show, attend, and tell method that captions the image while attending on the parts of the input. So it is also claimed by some to be faithful. And more modern method, NLEs, which is a combination of a convolutional neural network with transformer that generates the explanation. The first question which we have asked is whether the output explanations are plausible. To address this question, we had 10 human annotators, 5 experts and 5 non-experts. By an expert, I mean a person who published at least one paper in the area of explainable artificial intelligence, but not necessarily about the natural language explanations. We asked the annotators 5 questions: whether the explanation is fluent, whether it is easy to understand, if they find the explanation convincing, and whether after reading it, how well they are understanding the decision process of the model. And also, we added some additional question about the overall quality of the explanation. As you can see, except from the comprehensibility, our method obtains significantly higher scores than the other methods. And the result about comprehensibility has a very good explanation, because SAT produces explanations in form of phrases. So the typical length of the explanation has from 5 to 8 words, whereas our method produces several sentences. So it's not of a huge surprise that the annotators decided that it's easier to understand a short phrase or a shorter sentence than, like a 3 or 4 sentences. It's getting more interesting when we split this result for the experts. And interestingly, experts ranked higher all the explanations provided by the all methods. They were more happy with the results than non-experts, except for one question and 2 methods. So the only questions where the experts were not so happy, or at least less happy than the non-experts, were the questions about how well they understand how the model works. And only our method was for the experts, providing an interesting insight into how the model works. Okay, so the second question: are our explanations faithful? Because despite the fact that we have asked, the people if they think they understand how the model works, we are still evaluating in this way the plausibility, whether the user trusts the explanation, whether the user thinks he had, get an idea how the model works. So how to evaluate faithfulness is unfortunately an open research question. There are several, techniques proposed. At the last ACL conference, there was a paper that proposed two tests for faithfulness. The first test was producing counterfactuals by inserting words and checking whether these words, which clearly influence the decision, are mentioned in the NLE. And the second method was checking whether the reasons which are given in the NLE are sufficient to maintain the model's decision. In general, it is also believed that the human annotators cannot assess faithfulness since they don't know how the model works. This is something which I commented already. And here it's important to notice that our pipeline approach has an interesting property, that we can evaluate faithfulness of its parts. So, for instance, LRP is a highly faithful method which was already demonstrated in various papers. And then the only, let's say, point where the explanation can be less faithful is if the meaning representation to text conversion goes badly. And in our study, we asked the annotators to compare meaning representation with the output text, and found that only 8% of the NLEs contained some hallucinations, and otherwise they were faithfully following what is in the meaning representation, which was constructed based on the LRP. About the 2 tests for faithfulness which was recently proposed, unfortunately, the first test, which concerns inserting words to the input, is not applicable for images because, well, we cannot add the images we cannot add insert words into the image. But what we can do is we can check whether the reasons in an NLE are sufficient to maintain the model decision. In our experiment, we asked the user to read the explanation and then remove from the image the reasons, the rationales for the decision. So, for instance, the explanation said, okay, this is something because, well, there is water in the image. So the annotator was painting all the water in the image with the white color, to remove this rationale from the image. And in this way, we're checking whether the reasons which are given in the explanations are really the reasons how the model works, how the model performs the decision. And well, the decision was changed for 88% of examples, and the average decrease in probability of the original predicted class was about 45%. Interestingly, the explanations for such images were changed in 100% of the cases, and the changes were quite significant. Why? Because on average, 78% of the neurons indicated in a mimic representation were changed. So not only the explanations were different, but also the change of the change in the let's say content of the explanation of the rationales which were given in the explanation were also very different from the original ones. Okay, so we have showed a relatively simple pipeline approach that produces both plausible and highly faithful explanations. The model works with any convolutional neural network, and it doesn't interfere in any way with the classifier training process. The method also don't require a data set of reference explanations, and since it's a pipeline approach, it can be easily updated with, for instance, better neuron annotation tools or other techniques which a given person prefer. And that concludes my overall talk. We showed two simple techniques for producing more faithful NLEs. The first technique was adding a coherence enforcing task to the explainable model. The second one was a pipeline approach for generating faithful NLEs. There are still some open research questions. For instance, how a good textual explanation looks like, how much information should it contain. Our experiments with experts and non-experts demonstrate that there seems to be a disagreement between these two groups, how a good explanation looks like. So maybe it's one issue that is worth investigating. And the second question is how to construct similarly faithful NLE meaning representations for other tasks, for instance, for recommendation, text classification, etc. And if you want to know more details, you can take a look at these papers, and I'm happy to take some questions.